get started, and I have just just brief announcements to those who have joined us already. This is, if you don't know where you are, this is the March meeting of the East Bay Astronomical Society. Thank you all for coming. And before I turn it over to Dave and our speaker for tonight, I just want to remind everyone that the Chabot Space and Science Center has once again opened to the public and is open on Friday and Saturday nights for telescope viewing. Our telescope makers workshop that we hold on Friday nights is back in business as well. We actually had a lot of students come out of the woodwork after 3 or more year hiatus, and we were pleasantly surprised to hit the ground running on the workshop. And so we've got a full complement of students and projects being worked on in the center once again. That's very exciting to me and to everybody who's involved in that project. The Science Center is not open in its normal weekday hours, so don't expect to go there on like a Wednesday morning and be able to go to the Science Center and see the new exhibits. You have to kind of do that on the weekends and plan your week around that. They're starting school groups again, I believe, next week. So I think on Wednesdays and possibly one other day. I think it's like Mondays and Wednesdays or Tuesdays and Wednesdays. They're going to have daytime school groups again. So, it's all very hopeful, and hopefully we can keep on that trajectory and continue opening our center to the public as things get a little bit more back to normal. I guess that's really it for announcements. Hope everyone is doing well. And Dave, I'm going to turn it over to you for introductions, and you'll see me a little later when questions and answer time arrives.
And Kimberly, you can see that I'm notoriously long-winded, so I shall try to.
Well, I have the hook.
So I'll try to be concise and not to. I have to always remember that the meeting is not about me, it's about the speaker. And so Dr. Kimberly Ennico Smith is a research astrophysicist at one of our favorite places, and she's a planetary scientist too, over at NASA Ames. And she has worked on a bunch of really cool stuff and knows a whole bunch of people who we know, and who, for example, Sophia. She worked on Sophia, she's worked on L-Cross, which a lot of us tried to observe the impact into the moon. Unfortunately, we didn't see it, but hopefully they got some good data from that. That was a wonderful mission. And she's also worked as a deputy project scientist on New Horizons. So I bet you she knows Jeff Moore and a bunch of our other friends on that wonderful, wonderful mission, an incredible mission. And she's now working on this amazing mission, something I'm very, very excited about. The Viper mission to the south pole of the moon to look for water on the moon. And the implications of that are really amazing if you think about how we could use water at a base on the south pole of the moon. So Kimberly, without any further ado, by the way, Kimberly, I'm going to insist that you show your dress to our audience, because it's one of the neatest dresses I have ever seen in my life. I love this dress. Without any further ado, Dr. Kimberly Ennico Smith.
Okay, Dave, I'll take you up on that. Yeah, I can't remember where I found this dress. I think I saw it on a colleague at a conference, and actually it wasn't the moon, it was Titan.
Really?
And it was brilliant because Titan has an atmosphere. This is the moon of Saturn. But anyway, I digress. All right, okay. The moon, the dress.
Okay, please. That is so cool. Mare Crisium, serenity, tranquility, fertility, all there.
So, oh yeah, and if you guys are moon spotters, and of course, I wish I was there in person with you all. And I hope all of you are staying well and sane and as best we all can. Right. I will keep going, I guess. Right. So, hello. My talk tonight with you all is about the motivations, the design, and challenges of exploring the lunar poles and the significance of the mission Viper So thank you inviting me to share you the story of this mission. But of course, I'm speaking on behalf of a team of scientists and engineers to make this possible. But we have to acknowledge something which happened yesterday. Hold on. The rocket, the objective. If you weren't following the news, the rollout of the Space Launch System, the SLS, this is a rocket. It is not an animation. It is on Launch Pad 39B in Kennedy Space Center. It is being ready for what's known as a wet dress rehearsal. They're going to fuel the rocket and practice the countdown, but not actually launch it. The launch of this rocket will occur probably in June. It's a mission called Artemis 1, and it's all part of the Artemis program, which we'll touch on a little bit later. But beautiful picture. What a great shot. Okay. I entitled the talk about the story of water on the moon because there's a lot of chapters to this, and I like thinking of things a little differently than other scientists, but telling a story. But 1609 is a significant time in our understanding of the moon because this is the first recorded impression of the moon through a telescope. So the first realistic depiction of the moon in history, it's Galileo drawing his observations. The moon has mountains, it's got pits, it's got other features, just like the Earth. The fact is the moon is not smooth, which had been thought on for eons. So Galileo kept an open mind, he remained curious, and in doing so, he challenged the thinking around him and pushed our knowledge of the universe forward. So tonight from Oakland, if your skies are clear, the moon is a waning gibbous. So it was just full yesterday. Tonight should rise around 9:10 p.m. local time, so a few hours from now. It'll transit, that's the highest point in the sky, a bit after about 3 a.m. And then set just a little bit after sunrise. So the image you see here is from Stellarium, which is a free open source, excellent, awesome planetary program for your home computer. So I set it for Earth coordinates, Oakland, California, 10 p.m. local time. And as our theme tonight is water on the moon, how about a nod to moon water, but in the wrong way? The near side of the moon has the side that faces us is the most noticeable dark features, the mare, plural maria. It's Latin for seas. So they were erroneously named by 17th century Western astronomers. They are not seas. They're just huge basins containing cooled off lava flows. There are about 20 of these on the moon. But perhaps your imagination does not see the seas. Perhaps you see the man in the moon or the face in the moon. Or as we're coming into springtime, you see the rabbit in the moon, yes. A rabbit pouring the mortar and pestle, making the elixir of mortality. But fun aside. Our story continues. The second leap is the start of the physical exploration of the moon. It actually technically begins with Soviet Luna 2 that made the first hard landing in September of 1959, but then would follow several robotic missions and of course, famous human landing missions from 1969 to 72 from the Apollo program. The photo here is one of my all-time favorites. It's Pete Conrad Jr., the Apollo 12 commander. He is examining the robotic Surveyor 3 spacecraft. Apollo 12 landed on the moon November 1969. Surveyor had landed April of 1967, 2.5 years earlier. It's a story of using robotic explorers to check out the lay of the land first, next followed by humans. And way in the back is the lunar module Intrepid seen in the far back. I just think this is a fabulous story of how humans and robots together can explore just our planet and also beyond.
Yeah.
So in the second leap, in learning about the moon, this physical exploration, where did they all go? So we see our mare, just to orientate you are. I'll add in some names of the most visible craters on the mountains. And now let's put down where our robotic explorers went. And then the 6 landed human missions. So we are exploring the moon and we're getting samples and samples returned. Only covered at most maybe 4% of the moon surface, but this, even this is a small amount, we still learned an incredible amount about our nearest neighbor. In particular, specifically to our story of the moon pretty much got a dry reputation. Analysis of the rocks brought back by the robotic and human explorers showed no evidence of water. And even in the reports and the papers that came out, we're reading things like, are virtually devoid of water. There's no strong evidence, never exposed influence of water, absence of water, water-free. At the same time, chemical analysis of these moon rocks informed us that the Earth and the moon are made of similar material. And the years that followed Apollo, the concept of, how did the moon form, led to the development of the giant impact hypothesis, this common ancestor where a collision between the Earth and a Mars-sized object about 4.5 billion years ago led to the creation of the moon, we think, or the hypothesis says so. But it would rule out other hypotheses that were floating about. And, it's most likely the explanation for the formation of the moon. And in our story of the water on the moon, the impact was so fiery and violent, the scientists would just suspect that any water, whether it came from the Earth or that mystery object, would have boiled away for good. So it's still the leading hypothesis about how the moon is formed, but it doesn't still explain everything. There's still mysteries there. But the point in our water story is that the conditions were not right to keep water around. However, I find it fascinating when you learn about science, you stumble upon mysteries. So as an aside, even back then, there were some who suggested conditions existed for lunar water to exist. Here's a paper from 1961, Watson, Murray, and Brown. It's also the first suggestion of lunar cold traps, where lunar solid water ice could exist. More about that later. It is a nice lesson in the importance of getting your thoughts, your hypotheses out in the scientific literature, even if it goes against the current groupthink. But I digress, because with most good stories, our story gets a twist and new characters enter. So we've come to the third leap in our story. Water is now discovered on the moon and potentially in large quantities at the poles. Its presence continues to challenge the theorists who for decades computed that the moon should be bone dry. So after the Apollo program ended in 1972, we never stopped exploring the moon. So enter now the next generation of the robotic spacecraft that came in the 1990s. They have more modern instrumentation, they measured new minerals, and their orbits took a closer look at those lunar poles. Often those areas were not part of that first wave of exploration, more equatorial based. So meet Clementine. Its bistatic radar test revealed a curious finding at the poles that could be superficial water ice. However, the signal was not consistent enough, and it was also consistent with the fact that the surface could just be blocky and rough and rocky. So it was inconclusive. A few years later, Lunar Prospector enters the scene and makes measurements of neutrons, gamma rays, electrons, alpha particles coming from the moon, and in particular, neutron measurements that reveal that craters shadowed at both poles contained elevated hydrogen levels. This was the data set that started an exciting new dialogue about the moon. Lunar Prospector did map the entire lunar surface, but both poles, these are shown the north on the left and the south on the right, they would show a distinct elevation in the amount of hydrogen. But I mean, actually, if you look at the data, the spectrometer actually measured neutrons. So neutrons are generated by cosmic rays, and they're coming out of the lunar surface, the lunar soil. When the neutrons strike something about their size, a hydrogen atom, they lose a lot of energy. So the actual measurement was the spectrometer on board the spacecraft measured a suppression of neutrons. And then we're interpreting that to be the presence of large amounts of hydrogen. So the color code here shows purple for low neutrons or high amounts of hydrogen. And staying true to the spirit of Galileo, the community got curious and had an open mind. This neutron mystery led to a series of more missions in the early 2000s to measure the hydrogen and reassess the mineralogy. One mission in particular did a specific test of whether that hydrogen is in the form of water, H2O. That mission was LCROSS. I was very honored to have worked on that mission, and I was controlling the scientific payload during the descent and throughout the entire mission, and it was a fabulous experience. We deliberately crashed the upper stage of a rocket that would have been space junk into a permanently shadow crater at the moon's south pole that had this strong hydrogen signature. So that dark purple on those neutron maps. In fact, that's where we hit. X marks the spot. It was an impact experiment, and we tossed up 4 to 6 tons of material, and we made a crater, and we had spectrometers aboard our spacecraft, and we measured carbon monoxide, ammonia, methane, and simple organics, and most significantly, water vapor and water ice, and in large amounts. So LCROSS was a definitive game changer in our story of the moon water. So now we have the first direct evidence that a strong hydrogen signature in a cold location contained a lot of water ice. So our international next-gen fleet of missions have continued to reveal even more nuggets about lunar water. So meet the Lunar Reconnaissance Orbiter. It's still operating in the moon today. It has provided so much data about the moon. We have global topography maps, we have global surface temperatures, and even the measurement of some UV reflected light may indicate that there's ice on the surface of permanently shadowed craters. We also have Chandrayaan-1 that carried a near-infrared spectrometer called M3, M-cubed, and measured the surface water presence spectroscopy and reflection by sunlight. It and its successor, Chandrayaan-2, have made global moon water maps, revealing that there is more surface ice near the poles than towards the equator, but it's still a lot of places. We have Kaguya, the Japanese lunar spacecraft that's provided us updated maps of the moon's elemental and mineralogical composition, and then most recently China with its Chang'e missions, including 2 rovers and a robotic sample return. And specifically, looking at our story of the surface explorers, where's our map looking? So the 3 China missions are now shown in the red. They've actually landed a rover on the far side of the moon, which has been also revealing lots of amazing science. So to sum up this part of the introduction to the talk, the moon today has lost its dry reputation. We have learned that water concentrations are not uniform everywhere. The poles do seem to have a lot more of it. Yet, the different techniques reveal different water amounts, and sometimes they're not consistent. So we got a mystery there. We have that one single data point from the impactor, that the water ice is buried deep within the crater that was sampled. And we have a detection of water by SOFIA, an airborne infrared telescope, made detection of water in sunlight regions of the moon. This water is a bit different than the water ice buried in cold, dark places. It may be just water ensconced in glass beads and rocks. And clever scientists have now reanalyzed the Apollo samples, and they actually do show water. Specifically, though, they show hydroxyl, OH, in the samples as the folks were heating up the rocks and looking at the spectra. But the bottom line was the modern instruments in the labs today are much more sensitive. And these rocks do have water. It's just that the sensitivity. So sample return missions are the Christmas gift that keeps on giving. In fact, 50 years later after Apollo, we're still trying to tease out mysteries. And a paper that came out earlier this year, just about 2 months ago, the Chang'e 5 lander that landed in December of 2020 on the near side, it has now confirmed water in a rock in Oceanus Procellum. And the current thinking is perhaps this water comes from the lunar interior. So talking about water on the moon, and it can come from lots of places. So I mentioned the term permanently shadowed crater. From a sunlight perspective, the moon's poles experience pretty funky illumination. And this is an animation. Click on this. The poles are a long way from those Apollo landing sites, which are indicated with the numbers. This animation will zoom in towards the south pole of the moon, but the similar illumination conditions are at the North Pole as well. And they're quite different. The sun only gets a few degrees above the horizon, and it creates a geometry where long shadows are cast by topography, and the shadows can be 100 miles long. So as the sun is moving around the horizon, it's illuminating different parts of the terrain. And if you just pick out one point or stare at one point in this video, certain places never see the sunlight, and they're called permanently shadowed. And without the sunlight, those areas are very cold and may have been cold for most of the geological history of the moon. So it is to this polar region full of shadows where our Viper rover is going to go to look for ice. This unusual illumination, well, unusual, it's just how the geometry of the moon puts it. It makes the poles a very different place to explore than all our history of lunar exploration at the equatorial regions. So we are about to start the next chapter, the next leap in our water story. So this next chapter is all about ground truthing those orbital data sets. We are embarking on the challenge to map the moon at the rover, or say the human scale, to assess how much water is there, and also, is it acceptable? So this is the landscape that set the motivation for Viper. Viper stands for Volatiles Investigating Polar Exploration Rover. Viper is driven by two goals: to characterize the distribution and physical state of lunar polar water and other volatiles in lunar cold traps, and the regolith, the lunar soil, to understand their origin. And second, to provide the data necessary for NASA to evaluate the potential return of in situ resource utilization, ISRU, from the lunar polar regions. So let me tell you a little bit about our rover. It's quite agile. It's about the size of a golf cart, 1.5 by 1.5 by 2 meters. It will be rolling through a very dramatic lighting environment with those sharp, contrasting, and long shadows. You know, some shadows are, I said, hundreds of miles long. There are also unknown rock and crater hazards. Our knowledge of the terrain that rover will explore is only good today to hundreds of meter scale. So we're going to be in the dark. So we're equipped with cameras and lights. We have lights in the wheel wells to look for rocks and the terrain. And then we have lights up on a mast that does a 360. So a very challenging environment. The nature of the lunar soil, the regolith, is also unknown. Is it hard? Is it soft? It is churned up. Some folks may remember the big debate about, you know, would the Apollo craft sink in the moon? The robotic explorers that went before figured that out. That wasn't a problem. But in our case, we're going to places that haven't quite been explored and have had a very different history. But is the soil hard? Is it churned up? Is it trafficable? So the design of the wheels is unique. So each wheel has an adjustable suspension and is independently steerable. Some videos of the test article that have led to Viper's mobility design. So at the top, you see the Rover squatting, and then in the bottom, it's swimming to see whether it needs to climb out of fluffy soil. I'm using fluffy as just an adjective. Okay. So more about our rover. So I mentioned that the sun does not get high above the horizon when viewed from the lunar pulse. Well, guess what? The Earth doesn't as well. Here it is a time lapse of the Earth seen from the region where the Viper rover will go. It also doesn't rise above the horizon. This is going to be challenging for us because we're tele-driven. The rover's tele-driven. It can only be driven when in direct line of sight with the Earth, for the driver on the Earth to send commands for the rover to drive. The rover is also solar and battery powered. Yes, although the sun is low to the horizon, some of the sunlight can reach the rover, as long as there's not a shadow cast from a crater rim. So I'm just showing another animation of a rover path shown with the red arrow, if you can see, and how the shadows are moving in time. So the Viper's rover speed is about the same as the shadow speed. So Viper is often chasing the light with a shadow on its tail. The rover does carry batteries, so it can survive up to 50 hours in darkness. But this whole approach to exploring this unique and challenging lighting routine is about time and location. So since we're solar powered, we do need the sun on us. We can survive a little bit in darkness, but it means we are chasing actually we're chasing the sunlight, and the shadows come behind us. We're also traveling in very cold territory. In those areas that have never gotten sunlight, they can get down to minus 390 Fahrenheit or 40 Kelvin. That's as cold as Pluto. But it also has to enjoy its sunbathing to recharge its batteries. So it needs to go to an area of plus 80 in the sun, 300 Kelvin. So we have heaters and things to warm the electronics and a radiator to dump the heat. So this is a very thermally challenged rover, but we think it's pretty cool. It's a new type of rover to add to our interplanetary robotic explorers. Our Viper is shown on the bottom right. From a speed perspective, it's 5 times faster than the current generation of Mars rovers. Curiosity and Perseverance doing amazing things on the red planet. But it's much slower than the Lunokhod, the Soviet-era rovers of lunar past that was booking it. And then, of course, the Apollos drove their moon buggy that went even faster. But as I'll describe more later, we want to map a range of terrain types. And to do that, we have to go fast enough to get the mileage. And we also have to go slow enough to gather enough statistics along the way. So the science instruments aboard Viper, it's the heart of any mission. So the Viper measurement and mapping concept evolved after years of analog missions. So analog missions is where we take a rover with different types of instruments here on Earth and use them operationally together in scenarios. So what will fly on Viper is optimized for surface and subsurface moonwater mapping goals. So Viper contains a neutron spectrometer that sticks out front. I like to call it the Viper Bloodhound. It'll detect neutrons. Where there's a dearth of neutrons, this could be indicating of large amounts of hydrogen. So our neutron spectrometer could also be seen as the hydrogen divining rod. In the belly, we have a near-infrared spectrometer. It's looking at the surface to identify and quantify water and other volatiles through their spectral signatures. There's a camera with different lamps to illuminate the soil and assess the mineralogy, and a thermal radiometer to measure the surface temperatures. Because previous missions indicated that in order to do corrections of spectral signatures, you needed a good handle on how much was coming from thermal emission off the surface versus absorption by the species. We are also carrying a mass spectrometer to distinguish between 1 and 70 AMU, atomic mass units. So the instrument will be able to determine H2, which is AMU of 2, from OH, which is AMU of 17, from H2O, which is AMU of 18, plus isotopes. And isotopes can tell us about the origin of the water. It's coming from comets or from the moon itself, or maybe that mystery object. And then we carry a drill on board to drill down to 1 meter in 10 centimeter bites and measure the subsurface temperature. So the payload is integrated and analytically powerful. The mission design is a delicate recipe of that rover to get the mobility, those overlapping of the instrument capabilities, and an approach to modeling, a geostatistical approach to modeling. And so our key science measurements, sensitivity, coverage density, length scales, that's how parts are related to each other from a one-to-one in a distance, aerial coverage, variability, vertical coverage, and vertical sampling is how the approach of putting together this mapping mission. So how do we map those to specific observables? We think we have the right approach. We know there are going to be surprises. We're following mapping approaches that have been developed here on Earth by the USGS. When they go out to quantify something or new or something known in an previously unmapped area, you don't have the resources to drill every foot. You have to be strategic about where you drill. You have to be strategic about how you cover things. So when you want to quantify something new, or even if you know something but you're going into a previously unmapped area, we're trying to do this with a statistical approach, which I just find fascinating. A key part to this strategy is using temperature as a proxy. So our mission again is to ground truth those hypotheses about where the water is and how much is there. So from the evidence gathered to date, cold temperature is a good indication that water and other volatiles will stick around. After all, they're called volatile. Volatiles mean you easily go into the gas state and escape. Thermal modeling of the lunar soil predicts that the subsurface, even down to just a few tens of centimeters, can get pretty cold, even if the surface has been exposed to sunlight. And so the Viper mission is planned around this thinking, the ice stability region concept. So models are predicting a temperature where at or below that temperature, water will be in its frozen state. So under 100, 110 Kelvin. And it has been cold over geological time frames. So it should be still there. But we also have to take into account a range of processes that may be affecting the moon's water cycle. And there's lots of, this is a very active area in science today about actually a water cycle, where the water comes from and where it's escaping or going or getting retrapped in or what have you. So this ISR concept is broken into 4 categories for our proxy. We have the surface shown here in red. This is where water ice is predicted to be present on the surface, like a frost. And we think this is where they're located into those permanently shadowed craters. But then there's the shallow, shown in green, where water ice might be present in the top 0 to 50 centimeters, so half a meter. This is very active today because the moon has been pummeled and continues to be pummeled by micrometeorites, and it's churning of the soil. So it keeps ice around by burying it, but it also can excavate buried ice, and then it once gets to the surface and it vaporizes. So knowing how much ice is in that top half meter is going to really advance our understanding of subsurface water on the moon. Then we have deep. So deep is where water ice might be present in 50 to 100 centimeters down to a meter. Now, we would love to go deeper. In fact, many lunar theorists do hypothesize that the ice may be buried much, much deeper, like tens of kilometers. But the 1 meter distance was chosen for Viper because it's scientifically interesting and it's ISRU friendly. There are so many different ways to excavate buried lunar water ice. And the 1 meter depth seemed to be on average a depth to which several technologies are applicable. And then finally, there's the dry, which is basically no water is expected in that top meter. It could either be buried much, much deeper or just not there at all. So that's how we're bounding our sampling scheme. So then how about mapping? So now we need to find a path for the rover and its instruments that not only meet that power and communication constraints, we need to avoid being in shadow for more than 50 hours. We have to have the Earth in our line of sight. But we also have to visit all these 4 types. So shown here is an example traverse. And the concentric light circles just represent distances from a landing site. So the innermost is about 100 meters, the outermost is about 3 kilometers. So the example traverse is shown in green, dark green here. It covers about 13 kilometers in about 91 days. And the rover has to pause at the end of each lunar day to go to a safe haven, to keep its solar arrays charged when the Earth has gone below the horizon. And the Viper science team is right now looking at the pros and cons of these multiple traverses. The point is we got to cover the terrain. We need to visit those 4 types. We have to keep the rover safe. It's a highly constrained problem. But as we're, we're expecting the measurements as we go through the mission. So in the prospecting mode, the rover's moving about 10 centimeters a second. The science team is going to be getting real-time data on the amount of hydrogen, the presence or absence of superficial water, and surface temperature. And the science team on console in the Mission Operations Center at NASA Ames will get immediate indication of whether reality matches the predictions or where it does not. And then the team can in turn react and replan where the rover could go next. The 3 prospecting instruments really do work well together. So here's a schematic of trends that the Viper science team will be looking for as the rover drives. So the rover is moving along from left to right. The yellow curve is temperature, and it's lowering when the rover drives over that frost. The light blue curve is indicating the depth of the water feature from the infrared and the mass spectrometers, and it's showing it's peaking where the surface temperature is low. And then the red curve is indicating the neutron counts from our bloodhound. And the neutron counts are detected where they're low is indicative of a high hydrogen presence, but we can't tell you whether it's surface or buried or both, because it's just measuring neutrons, and neutrons are just coming from the surface. You don't know where it's coming from. But what's curious in this hypothetical example is that neutron count stays low well after the rover has passed over what might have been a frost region. So here is where the near infrared and the mass spectrometers are blind because they only see the surface. But we have an indication that there might be a buried ice layer. So that's where we have the drill. So there are times where we need to drill. This will help anchor our data. After all, we can't tell a difference between the shallow and deep region. So we have the drill on board. And 2 of the instruments, the infrared spectrometer Nervous and the mass spectrometer M Solo, their fields of view overlap onto the drilling pile. I'm going to show you a video here of a laboratory test where these 3 instruments are used together. And so we have a vacuum chamber that was filled with lunar simulant and infused with water ice and other molecules. And so the drill is excavating and it's dumping the pile. And then simultaneously, we are observing the pile grow, and also we're observing The amount of water, if it's present, and how fast it's sublimating could be measured. So the approach that is taken to measure the water at depth is the drill excavates at different bites, these 10-centimeter bites, and we're looking at it with our spectrometers and our cameras and telling you what is it, how much water is there, and at what depth it's at. So, all right. So I mentioned the Viper rover and its smart payload and the mapping and measurement strategy. So, but we still need to get to the moon. So introducing the Griffin lander from Astrobotic. So Viper is part of a new program at NASA where companies are providing a FedEx service to the moon. It's a different approach. It's fascinating. Our Griffin lander will place our Viper rover at our desired coordinates within an error, of course. But since our traverse planning is inherently dynamic and responsive, we have the tools to create new paths wherever we're placed. In fact, right now, the mission team is looking closely at 5 different landing locations. So an infinite number of monkeys can type out the words of Shakespeare. And yes, with a supercomputer, we can design thousands, hundreds of thousands of Viper rover paths, but it helps to narrow the choice. So last year, the team completed a study of multiple landing sites near the lunar South Pole. The landing area needed to provide a plausible surface, subsurface, volatiles, reasonable terrain for landing and roving, a direct view to Earth for communication, and enough sunlight for power. This is one of the reasons why we're not landing at Shackleton, which for those who follow closely, the Artemis program was one of the places where they might be landing. But we are going to an area on the western rim of the Nobili crater near the lunar South Pole. It's a rather high plateau, and so it's great for sun and calm. So so this is the area on the western rim of the Nobili crater where we are now doing that next step of where should we actually land and where should we drive. So let's take a closer look of this Nobili region. So the area the Viper will study covers an approximate surface area of about 36 square miles. 10 to 15 miles we're going to expect to traverse. So we'll traverse between 10 to 15 miles or 16 to 24 kilometers. There's a reference traverse shown there in pink. It's extremely attractive because it brings the rover close to 2 large permanently shadowed regions shown coming up soon in the light blue. So again, we want to be mapping and sampling these 4 different types. And in particular, we do want to get into these permanently shadowed regions where the water should be at the surface. So unlike the Energizer Bunny, the Viper has a limited life. So we're designed to land in late 2023 to go to the lunar South Pole, which is essentially southern summer. And like seasons on Earth, there are times where the sun is a bit too low on the horizon for too long, and the periods of darkness get longer than our 50 hours of battery life. So sometime in March of 2024, or maybe April, if the topography is kind, the shadows will stick around too long, and our rover will slip into a dark sleep. So maybe we will just slip into a dark sleep, or we will go like Thelma and Louise and go into the deepest, darkest crater within reach and rove and rove and rove and rove and take data in the darkness until we run out of juice. That decision has not been made. It all comes down to where do we find ourselves towards the end of our season where the sun has been favorable. But wherever Viper winds up, whether it's parked up on a hill or maybe it's down in a deep, dark crater, perhaps we might have that Apollo 12 Surveyor 3 moment when our Artemis human explorers come and check us out. So to sum up, our leaps in the story of water on the moon. 1609, the moon becomes a real place. We were able to touch it and explore it during that physical exploration of the moon and bring back samples. And how it surprised us in just the past few years, from frosts to buried ice blocks, the water appears to be everywhere, but its nature, its distribution is highly uncertain. So we're ready for this next leap. It's the Viper mission to give us that human scale detail of where the water is and how much of it is accessible. So with this new close-up and personal view, we can better piece together the science of water on the moon and begin to develop water maps that could tell us the best spots to harvest water. In addition to Viper, there are a whole bunch of missions to do this next step for water mapping on the moon. We should be seeing small satellites being launched this year to make more detailed maps of the water on the surface of the moon from lunar orbit. Also, some ISRU demonstration missions on some of these other commercial missions to the moon, using the Viper instruments to do some drilling and also do some scooping, and then of course Viper. So for the latest mission updates, please visit our website, www.nasa.gov/Viper. For you moon gazers, after all, Nobili is visible from Earth, although it has periods of darkness. I end the talk with a cool image taken from Tom Glenn in San Diego, and just a few years ago with a 9.25-inch edge telescope. So the Viper mission area is up on a high ridge. So we do expect a lot of moon gazers along with our journey of exploration and discovery to parts of the moon not yet explored. Thank you.
That was great.
Thank you.
Thank you. What an exciting mission. Yeah, I love it. I remember how excited I was about the prospect of water on Mars, and I thought how unique it is. And this is like going the extra mile, water on the moon. So we have some questions. Dave, before I present those, do you have any? I know you.
I have 4.
Okay, well, why don't you ask first the first one or two, and then I'll move on to audience questions.
Okay, my first question is, you mentioned that we don't have super high resolution images of the landing site. So I'm assuming that the Griffin is going to have some sort of AI so that at the last second it doesn't land on top of a boulder, tip over, or something like that. Am I correct in that?
You are. I mean, we are using everyone's been using the LRO maps, which can get down to even down to 5 meters, 20 meters, good resolution. The South Pole's the poles have been difficult to image with LRO, and so they're kind of spotty. But then also in terms of altitude, in terms of how high everything is, sometimes we have with the Lola instrument on LRO, we have altitude to 1 meters or 5 meters, spots on the moon. So there's gaps. Yes, the Griffin lander does have imagery and LiDAR, and we'll have the ability to find a safe place for it to land. But
for those who didn't know, the LRO is the Lunar Reconnaissance Orbiter, and it's a long-term mapping mission that's been very successful. So that's what Kimberly's talking about.
Yeah, and it's still operational on the moon today. In fact, they're going to be making as many images as they can of our landing area.
Oh, great.
And right up till we get there, just to help us with the coverage. All data helps. But yeah, when you image those poles, you get those weird, you get these lighting conditions that are very challenging. And if you don't catch it at the right time, you just have to start piecing together the story. But yeah, the Griffin lander will have some smarts on board to do avoidance to land us safely. Now, there are 2 ramps for our rover to go off. We have to decide which way to go off, and that will come down to which it might be the safest for us to egress from. And that again is also about, we don't really know the terrain. So this was one way to kind of easy way to put in, we can roll off in 2 directions.
Good. I also, before I ask my second question, I owe everyone an apology because I asked you to show your dress, but then I started exclaiming, and apparently I didn't realize this, the camera goes to whoever's talking and people weren't able to see your dress. So my apologies. So forgive me, I am going to ask you to show your
Hold
dress.
on, I've got to make sure she's spotlighted so the same thing doesn't happen, because I don't trust you to not talk.
Yeah, I don't.
You know, these are one of the things we wouldn't have to do if I was there in person.
That's right. I know. We're convinced. Oh man.
And then after that, I have a question.
Oh, you want me to show you the dress again?
Yeah, we got it.
And the story was I spotted this dress, but it was the Titan, the Saturn's moon Titan, and then the same designer makes one for Mars and for the moon.
There we go.
Thank you very much.
But the Earth is not drawn to scale. That drives me absolutely batty. So I'm like wearing science communication that's showing misinformation, but it gets a talking story.
All right. We have a question from, it was a 2-part question from Rod. With temperatures that cold, 40 Kelvin, is there concern about the metallurgy and fragility of the rover wheels and rough terrain? And similarly, has the drill bit been tested at that temperature? I would presume yes to the latter, but why don't you tell us a little about that?
Very, very, the thermal part of this mission is a huge engineering, challenge, but they've embraced it. So the drill has been tested at these very cold temperatures. And also it has both augering and percussive. So it's got ways to try to help it get out of, because it's hard to drill. In fact, InSight on Mars has had trouble drilling. The Apollo astronauts who tried to drill on the moon in different parts of the moon had difficulty. From a temperature point of view, we'll have temperature bits. Actually, the challenge for the drill right now is we might run hot. And our concern about running hot is we may vaporize our water before we make a measurement. And this is something to do with potentially being in an area on a traverse where the sun has been and we're not really cold. But yeah, when we're cold, we think it should be working better because it's been tested. The wheels, so the wheels are made of, oh gosh, I forgot what they're made of, but they are designed for the traction to go through soil that's hard versus soil that's soft. But yeah, the mechanisms have to work when we're cold. And also the wheels have been tested in a thermal vacuum chamber at super cold temperatures to just make sure that they work. But yes, we will be in extreme temperatures. And the Mars rovers are in cold. Mars is a cold desert. But yeah, we're going to be in super cold. In fact, when we do our first exploration of a PSR, it's considered it's high important milestone that we're going to dip our toe in first and then come out and then evaluate how everything's working and then go in again. Because we do, this is going to be in a lunar environment. How is the rover and all its mechanisms working in such cold temperatures? Then we'll have a little bit more confidence. We're not going to land in a permanently shallow region because it's just unknown. We're going to land in the sunlight, drive off the ramp, hopefully avoid some boulders. And then when we get to that first permanently shallow region, we are just dipping our toe in and monitoring that temperature like a hawk.
Yeah, literally putting your toe in the water.
Yeah.
Yeah.
A cold water,
Very cold
the
water.
polar plunge,
Yeah, for sure that. Joe asked the question, do we expect the terrain in the permanently dark areas to be consistent or similar with the areas that are exposed to sunlight? I mean, or is there just a bunch of guesswork going on there, or is there any reason to think that they may differ?
They shouldn't differ because everything should be hit by micrometeorites at the same rate
At the same
wherever
rate,
you are. It's just that the unknown is this temperature, which may be hiding these volatiles and other molecules around. And once if that changes the nature of the regoliths, we don't really know. We don't think it should, but if you have, you have contaminants, you have something different. Is it possible that's changed the behavior, the surface adhesion, the tension, these properties? So learning about the geotechnical properties of the regolith, especially if it's in shadow versus sunlight, might tell us something. But to first order, it's supposed to all be kind of the same. But we won't know until we go, and we've never been to this part of the moon before.
Dave, you had other questions?
Yeah, another question was, I remember very clearly on Apollo 14, the difficulty that the astronauts had in drilling into the soil. And you had mentioned that briefly. You'd mentioned percussive and I think something else. What exactly, can you describe, go into greater detail as to what mechanisms you've gone into to avoid that problem of the drill bit jamming in the soil the way it did on those missions?
Yeah, so the drill is built by a company called Honeybee Robotics, and they've been building drills that have flown, been in the Antarctic and the Arctic and in various different dress beds. And then one's going to be flying to the moon on a Prime 1 mission later this year. But they've come up with, and they've done a lot of tests in thermal chambers with lunar simulant, which is the best we have, and they're choosing to use hyaline material, which is what we're expecting to see at the poles. And they're doing the compactness, but it has a rotary percussive. So it's got a rotary and an auger that's going to rotate, and then it's going to have a hammer in case it gets jammed. And then it's going to be operating in bits. So the drill comes and it lowers itself, and it's only going to drill a certain amount, and then it's going to pull itself all the way up. Mm-hmm. And then it's going to go down again. Mm-hmm. And then it's going to come up again. And if it has any issue, it'll stop, and there'll be a way for it to do some extra vibration. In fact, we're going to do an extra science experiment by using the drill as a seismometer. Oh. And so then we can listen to it with the accelerometers on our IMU, so that we can try to maybe figure out, we're not going to be there long enough to experience a moonquake, which is rare, but we're only there for 100 days. So we're going to have artificial moonquakes to try to see whether the soil, is the properties of the soil. But yeah, it's going to go up and down a lot. And each time it's going to excavate what's inside the drill and come out a chute. So it's not going to always, this is supposed to help with the clearing. Yeah. So there's a lot, I'm not an expert. I'm just kind of paraphrasing what I've been listening and learning about, but it's after several years of engineering tests in chambers, tests out in the wild here on Earth. And we're really looking forward to the first test on the moon with the Prime 1 mission, which will go to, actually it's going to the polar regions. And so that's also going to be exciting. To see how that all works. But yeah, so it's drilling is right now it's like a really long, it's somewhere between 5 and 8 hours to do the whole drilling mechanism. And then we have pausing, and then we want to make sure we get the temperatures. So it is not a very fast activity. So we're talking, good 8 hours to do the one drill hole. Okay. And the astronauts had these handheld drills, and I think they were more of an auger rotary one. Yeah. And they didn't have this extra percussive aspect.
I remember watching this. I was at Stanford at the time, and the professor, I think, who designed that experiment on Apollo 14 was Professor Kovacs, if I remember correctly. And one of his grad students was right next to me while we were watching this. And of course, it was not successful. The astronauts practically killed themselves trying to drill these hand drills into the soil. And he said, boy, Professor Kovacs is going to be really upset about how this turned out. Yeah. It was extremely hard.
Frank asked a question about back in the early 90s and following that, the Messenger probe to Mercury, there were several observations that suggested water in the polar regions of Mercury. And to what extent were those observations used to hypothesize what's being explored now by this mission on the moon?
Oh, great question. Yeah, the fact that potentially areas on Mercury, which is really close to the sun and gets really hot, there are parts of them that are permanently shadowed, and so they are very cold. Mercury and the moon have a common share a common feature, that they're an airless body, right? They don't have an atmosphere. And so those measurements and the moon measurements from orbit have been used together to help with the modeling and the hypothesis about escape and retention. But we have to send another mission to Mercury to go to the surface of those permanently shadowed regions to see if it's true. It is, I mean, the conditions seem to be right. And if there was a lot of transport of water to the inner solar system and these places are cold, lunar trapping can occur. These cold traps can occur. And if you have this gardening, this things hitting, the surface, you can bury it and it could still be there. So yeah, that's a fascinating comparison. It's just helping out with the modeling. But yeah, that's
Okay. Let me see if there's any questions on our Facebook from our Facebook viewers. I actually don't see any. So Dave, did you have any other questions? And yeah, you always do, but you said you had 4, and I think you've asked 2 or 3.
I have another one, and this is, I wanted Kimberly's opinion on this because there's been a lot of discussion about what to do with the water on the moon once we get there. The assumption is that we're going to send people up there very soon, that we're going to build a base there perhaps, and that we're going to start harvesting the water. And there are various arguments as to what to use the water for. And one of them is to electrolytically disassociate the hydrogen and oxygen and use it as rocket fuel. And some people got very upset about that and said that's sort of wasting the resource. I'm wondering what your opinion is about this, Kimberly. How do you think we should use the water once we find it?
okay. Well, I mean, yeah, there's many uses for the water. I mean, the whole premise of in situ research utilization is so you don't take it with you. Can you use what you have, what nature is giving you? Mm-hmm. And certain things are destructive, use only once, and others are recyclable, reuse, repurpose. Making rocket fuel is one use of the water, just even turning it into oxygen for breathing or other activities is useful. Or maybe the water is best used for radiation shielding. I don't know. I would love to know that we have more experiments on the nature of the water. To give us a sense of where it might come from, because this also could tell us impurities in the water, and that could actually set you down a different path on how you might excavate it. And depending upon the use case, where do you find the water? If it's in large chunks, maybe it makes sense to do the one use only for rocket fuel. Mm-hmm. Or does it make sense if it's more in you got to harvest a bunch of, rake it through, some mechanism. Maybe it's used in a different means. So it's sort of about the amount and how accessible it is and where it can be used for your program. So I'm hoping that, Viper's there to be that first step to at least tell us where the water is, ground truth our thinking. I mean, the models don't agree with each other how much water there is or where it is. So we're going to get, and then it needs to be followed on with another mission to keep, and also the Artemis program will take samples and continue the story. And then you have to do all the engineering to excavate it, and then you excavate it smartly. What's amazing about space exploration is it's so challenging to do anything.
Yeah.
So if we develop these techniques to harvest water on the moon and recycle it and repurpose it, all of that technology can be back here on Earth. I mean, we can be able to extract water from the driest places, or reuse it or purify it, or use it in a different way, because we actually have solved that engineering challenge in a very harsh environment. Yeah, long-winded answer. My hope is we'll do it smartly, depending upon what we learn. The more we can reuse a resource over and over again, it's just a win-win for many generations. But it does come down to the use case. What do you really need it for?
Yeah.
Maybe our rocket should be powered by something else, although hydrogen and oxygen is the most common. But perhaps we found a different source for that, and we would rather use the water for something else. So I think it all comes down to that bigger picture. But it is just fascinating that there's still water on the moon. And there was someone in the chat early before the talk had quoted someone about how the moon wasn't going to be dry. I just think that's fascinating that it just stumps us. This is an airless body. It should have, evaporated, escaped. Yeah. Wow.
Yeah, what you read was a comment from Bob Garfinkel, who is the author of the 3-volume set Lunar Cognita, which is a beautiful set of books all about the moon. And he quoted Ralph Belknap Baldwin from 1949 as saying, "The moon is undoubtedly one of the driest places in the universe, but the story of the moon is not dry at all." So I love that. So thank you, Bob, for that. And I think on that, we'll probably close for the evening. And thank you so much for joining us tonight, Kimberly. It was good to see you. And I hope you return for more programs at Chabot.
Oh, Rich, I'm seeing that Steve Matthews has raised his hand here. Did he?
I don't know what that means, and if he has a question, you should put it in the QA. Here it is. Okay, it just popped in. How do you tell the difference between D2O and H2O with oxygen 18? So that would be deuterium instead of hydrogen.
Okay, so deuterium has an extra neutron.
Yeah.
So it has a neutron is just a neutral charge. But it has a mass. So it will have a slightly different mass. In fact, the challenge for, I think it's D2O, is that it has the same atomic mass unit as argon. Is that right? There's another trace gas that's going to make things a little difficult for us.
Oh, and distinguishing which is which will be a problem.
Yes.
Yeah,
so
okay.
you're gonna be so you can't, because they both will have the same signature. So then you use the mass spectrometer, tells you the mass, but then you use the infrared spectrometer to see if it's got a bonding motion or a bending motion that shows up as a spectral signature, and then you can tease out. And then when we get to the water ice, the shape of the band will also tell us in what form the water might be. I don't believe our spectrometer has high enough spectral resolution to distinguish between, say, amorphous and crystalline, which is a slightly different shape to the band. But we're not only expecting to see one type, but we're going to still detect water. But yeah, sometimes you have to use different instruments to measure things. But we're going to have a couple of places where it could be one of two things, but then we'll take some.
Yeah, and you figure that if you can't tease it, if you can't tease the data apart, it will justify another mission to
a different instrument, a different
with a different set of instruments to make that distinction there.
Yeah, in fact, one of the interesting things is, if there's if we just find everything's dry, that itself is important. because this means we might have been misleading ourselves in the interpretation of the orbital data sets. I mean, that's where, certainly go into those permanently shadowed regions where everyone is mostly confident that there's water there. But we could, these this shallow and deep, I mean, that's a model. And we're just going to drill. And if we keep on getting dry, that is good data. That is good knowledge.
Yeah.
But yeah, there's going to be mysteries, and it's not the suite of instruments to solve everything, but it's that first step to kind of have different eyes looking at things. And that was also designed in case one of the instruments wasn't working, we still had a backup instrument to keep us going. So there's all that play in part to but yeah, no, I wish we had a ground penetrating radar on board. I wish we had other type of instrument that uses lasers that allows us to actually, geodate things. Would have loved to have more of a scoop, although we might use the wheels to kind of drag things along. There's some kind of ideas we're thinking about of, running over the drill pile and running over doing things like that, but it all comes down to whether it's safe and all that. So what could you do with this tool set you've got? But yeah, no, determining deuterium from the hydrogen, we think we've got that with the 2 spectrometers to separate
Great.
the two.
Interesting answer. All right. Well, on that note, once again, I'll thank you for joining us tonight, and everybody who asked questions, thank you much for your questions, and we will see you next month.
Rich, I just want to say that I got a message from my wife, and she told me to say how much she enjoyed the talk, and she's the one who wears the geeky astronomy clothes in the family. So we're going to be getting a new dress pretty soon.
Okay. Well, thank you all for your attention and your questions, and keep following us along. And the moon story is not over. I'm ready for chapter 4 now.
All right. Yeah.
See what we're gonna find.
Yeah, so we
But
all
thank you
are.
all.
Yeah. All right. Well, take care,
Thank you very
Kimberly.
much,
Bye-bye.
Kimberly. It's a wonderful and amazing talk.